Hey guys, this is Professor Janacek, and I would like to show you an application of line integrals. The application I want to take a look at is work of a vector field. Work is simply equal to the line integral over the path C of f dotted with t ds. You'll notice that is simply the line integral of the vector field. So work is the line integral. How simple is that? Let's take a look at an example. Let's find the work required to move an object along the line segment from -1, 0 to 0, 8, and then from 0, 8 to 2, 8 for the force field F is equal to xy. So we'll first remind ourselves that work, this line integral, is the same as the regular integral from a to b of f dotted with r dt. So I can take a line integral and rewrite it as a regular integral. Now let's first go from -1, 0 to 0, 8. Well, let's see. If we know that, let's see, R1, I'll call this, since this is our first situation, R1 is, let's see, t minus 1 and then 8t. Remember how to find this. Remember R naught is the vector going to the first point, and then v is the vector going from the first point to the second point, and then of course it's R naught plus vt. All right, so then what about R1 prime? Well, R1 prime is 1, 8. Oh, and you know what? I totally left this off. That should actually be, as we'd seen, this is R prime dt. Oh, that makes much more sense. So when working this line integral, it's probably good to remember that we can write it as a regular integral. Okay, so that's why we need R1 prime. And then, of course, f evaluated at R1, not R1 prime, but at R1. Remember, f in this situation we have is the vector field, the force field xy, or vector field xy. Evaluating that at R1, again, not at R1 prime. Oh, that's simple enough. That just gives us the vector t minus 1, 8t. All right, so that would allow us to set up the work from the first, within the first section. Also notice for this that t does go from 0 to 1. Make sure you remember how to do that. It may have been a while since we've looked at that, so I'm going to integrate from 0 to 1. The dot product between f and R1 prime would be 1 times t minus 1 plus 8 times 8t dt. We'll get to evaluating that in a second. You could do that now if you'd like, but I'm actually going to do all of these at the same time. So now let's take a look at going from 0, 8 and then to 2, 8. So this will be R2. Again, remember how to find this r value. It's r naught plus vt. R naught, of course, is the vector to the first, from the origin to the first point, and then v is the vector from the first point to the second point. So that ends up giving us what, 2t and then just times 8. So r2 prime is the vector 2, 0, and f of r1, I'm sorry, of r2 is simply the vector 2t comma 8. Again, f is just xy, so it's really just kind of a repeat of r2. Not always going to be the case. Make sure you remember how to evaluate f at r. And then again, our t values in this situation do still go from 0 to 1. That's going to be very convenient. So W2, this work for the second situation, again, will integrate from 0 to 1 of, oh dear, leaving off this notation, that's a prime here, of f dotted with r prime. So that gives us 2 times 2t plus 0 times 8t dt. All right, so now to find the work, the total work, simply work from the first situation plus work from the second situation. So we can write that as one big integral from 0 to 1 of 1 times t minus 1 plus 8 times 8t plus 2 times 2t plus 0 times 8. Integrate with respect to t. We'll simplify this just a bit. Looks like that's going to give us 65t oh, no, that's actually going to be, let me go ahead and put them together, 69t minus 1. Integrate that gives us 69t squared over 2 minus t. Evaluate that from 0 to 1. Gives us, common denominator, 69 minus 2, 67 over 2. Well, that wasn't so bad. Pretty nice. Again, the work of a vector field is simply the line integral. Very, very simple. I want to talk about a couple other ideas that kind of follow from this. First off is the idea of circulation. It is the amount of force that pushes along a closed path. So if you're looking along a path, again, a closed path, along a closed path, and I'm looking at the force that's pushing along that. Right, that's what we're looking at. That is circulation. You'll notice that circulation is the line integral of f dotted with t ds. All right, simply the line integral of a vector field, which we'll write as the regular integral from a to b of f dotted with r prime dt. And then flux. Flux is the amount of force passing through a surface. So we can imagine this as we have our surface, oops, we have our surface here. The flux is the amount passing through that. It could be going in or out. going through that surface. And the way we determine this one, it's the line integral of f, dotted within ds. Remember that n is the cross product of t with k, which looks something like that. Remember how to evaluate that. This does end up being a vector value. Notice we are getting a vector value for this second one. So we have n ends up being, again, a vector from computed using that determinant. All right, one interesting thing about this, though, if f, say we let f equal, we'll just look at it in R2 as f comma g. We end up, for this one, this gives us the integral, the regular integral from a to b of f times x prime plus g times y prime dt. However, flux, again, if you look at how to compute this n value and then dotting that with f, what you actually end up getting, this is fascinating, I think, computationally how this all works out, you end up getting the regular integral from a to b of f times y prime minus g times x prime dt. And again, it's all, if you just simply take a look at how all of the computations work out when finding n and then dotting that with f, that's just really fascinating that circulation and flux have very, very similar but also significantly different regular integrals. Well, there you go. Enjoy.